Hi everyone, hope you're having a great conference so far. Today I want to talk to you about how we got started doing product classification at Shopify. I'll start by telling you a little bit about myself and the company. I'll walk you through the problem we were trying to solve or the business case, what almost immediately went wrong as we were trying to solve it, and how we got around the different problems we encountered, show you my solution, and describe some examples. A few words about myself. So the Hebrew name is a bit hard to pronounce, but I go by Izzy. I've been working in Berlin for Shopify for the past 3 years. I'm a mathematician by training, but a big believer in getting things done, which is basically a company motto. I've worked in multiple disciplines, multiple industries, company sizes, and if you want to find out more, feel free to reach out to me after this. You can find me on my website, Twitter, or LinkedIn. So a few words about Shopify. If you were to ask me a few years ago, I would have probably told you that Shopify is one of the biggest companies that you've never heard of. Although I think that has changed a lot during the past year of the pandemic. The company offers an e-commerce platform for entrepreneurs to start, grow, and manage their businesses online and offline. And this means that the company offers a lot of different services, from the web front end to payment processing, to different aspects of store management and logistics. But what we're going to focus on today is a part of the company called Oberlo. Oberlo is basically a catalog aggregator, meaning that from the one side, we have a lot of suppliers that can upload products into the Oberlo catalog. And from the other side, we have Shopify merchants that can access the Oberlo catalog and very quickly and efficiently import products from the catalog into their stores and almost immediately start selling them. So we facilitate this kind of communication between suppliers and merchants. And because we have different suppliers working inside one catalog, this creates some problems. So this all started with our catalog manager coming to me with a very, very simple question. What was the best selling product on the catalog? And this seems to be a pretty straightforward question, right? We have product entities or SKUs, just find the ones that are, making the most money, and that's it, right? But not quite. If you look a little bit deeper, you realize that a lot of these SKUs actually represent the same, let's say, physical product. If you look at this example, it's a Valentine's teddy bear. A lot of different variants exist, made by different producers, sold by different suppliers, but they're all actually the same teddy bear. If you look at the data, you will see different product entities with different sales over time, but if you aggregate all of them together, you get a very different picture. For example, I think 7 out of the top 10 products that we had in the catalog, without this kind of aggregation, we wouldn't have seen them in the top 10. So it means that sales were spread around small products over time. And if you don't do this aggregation correctly, you get a very skewed picture of the KPIs on the platform. So you hear product, images, similarity. I'm sure we all went through at least one of these, tutorials or textbook cases of image similarity. And this seems to be a pretty solved problem, right? I mean, we take a neural network that can give us labels or maybe embeddings. We take a similarity measure and a clustering algorithm, and then extract labels and embedding, maybe use the labels or maybe use the embeddings to calculate similarity and then run a clustering algorithm. And then all we have to do is report, the new KPIs on the clustered entities. And we're pretty much done, right? Well, unfortunately, in reality, things are a little bit more complicated. So, like I said, if you look at the textbook examples, the digits or the fashion data sets, nice, clear images against a white background. Not in our case. In our case, images can be pretty messy, meaning that they can show something pretty complicated. I mean, is this the sweater? Maybe the phone? Or maybe, in this case, it's actually the phone cover. Pretty hard to tell, right? Or is this the shoe? Maybe some kind of shoelacing product, or maybe it's actually the sports watch? Really hard to tell. We have another problem where things are designed to look like other things. So in this case, yeah, I can guarantee you we don't allow the selling of live pets on the platform, but any labeling neural network will tell you that this is a snake. And it's kind of true, right? But it's really hard to tell that this is actually a potted plant. So it's another challenge. And from the other side of it, we have cases where we don't even have labels. So, I mean, what is this even? There is no label for this. Well, again, this was what was predicted for this. It makes no sense. Or something like this, which I don't even know what this is. So this is not some kind of outlier, or maybe something that happens once every, I don't know, month. A few thousand of these products were onboarded to the catalog overnight and started selling pretty well. And we didn't even know what they were. I mean, you need to look at the product to understand that this is actually something called a room aromatizer. You put perfume inside and it spreads across the room. They come in all different shapes and sizes, and it's really hard to know that all of them are actually the same thing, right? So in order to try and solve this problem, we decided on a few guidelines in advance. And this is kind of a checklist that I like to go through on almost every kind of large-scale project that I try to tackle. The first and maybe most important part is scope. I mean, yes, we can start by processing and labeling millions and millions of images, but can we actually bring value with the smaller subset of the problem? I think it's something that's almost always true, where you realize what you're trying to solve halfway through maybe the second iteration of trying to solve it, right? I think we've all encountered this case where you learn a lot of things as you're solving the problem. So working on a smaller data set and being able to iterate fast was really, really important. The second kind of guideline is domain knowledge. I mean, yes, we can use images and kind of blindly send them into a neural network, but if we know something, if we can add information, if we can add more of our knowledge, the supplier's knowledge or the merchant's knowledge onto the problem, I want to say from my experience, this is almost always the secret sauce that gets you from like a good solution to a great solution. So we wanted to make sure that we utilize whatever we know. Image similarity still remain the main driver. You can ask, well, why didn't you use product descriptions or labels or something like that? Well, if you think images were a problem, our metadata was even more problematic. We will get to it one day. And the fourth principle, well, we're not married to the tool itself. This is not a Kaggle competition or homework assignment. We wanted to make sure that we use the strength of deep learning, the part of the recipe that works for us, and work around the parts that didn't. And finally, this was a small scale effort to begin with. I wanted to be able to move fast. So I think it was clear from the beginning that I wasn't going to try and train my own network. This is, again, an expensive, lengthy exercise. The idea was to try and see how far we could get with out-of-the-box solutions. So let's talk about scale. Like I said, millions of products, tens of millions of images, but this is where domain knowledge started playing a really important role, because talking to the catalog managers, this kind of back and forth conversation that we had, we very quickly realized, wait, we might not need to classify everything. How many products actually have sales? How many products actually have any interaction within, let's say, the last year? So apparently, yes, we have millions of products, but only a few hundreds of thousands get any interaction. And if you follow the money, then 80% of the money was covered by around 10,000 products with under 100,000 images. And this was great because this is something that can fit in my laptop, right? So as I said before, learning faster and iterating faster is a key component in being able to improve and adapt your solution. So domain knowledge helped us not only with reducing the scale of the problem, but also with solving maybe one of the most difficult issues we had, which was image quality. Because again, if you go back to the textbook solutions to this kind of problem, okay, take some images and try and label them manually for quality, or try and find some kind of sophisticated solution, maybe something like the size, the ratios, the histogram, white balance, all these kind of things that you can try and figure out or rank images by quality, and then train a neural network to predict image quality and choose only the good ones. Again, a very lengthy, time-consuming exercise. But when we were talking to the catalog managers, they almost immediately told us, look, you're not the only ones that have this problem. Our merchants have exactly the same problem. And what do? Well, they pick and choose. So they basically filter out the bad images when they choose which images to display on their website after they import the product from the catalog. They choose good images. They remove banners, they remove size tables, or they remove images that are like too complicated. And what we had in our hands was actually a crowdsourced filtering effort, which we could use. And instead of going to the textbook solution, we ended up just picking the images that our merchant picked for us. So this was a really, really great outcome. The image quality dramatically improved, and we're able to move forward with much more certainty that we're not in a garbage in, garbage out situation. Another place where domain knowledge really, really helped was with the similarity itself. So, like I said before, machine learning is almost, I want to say, a must today when you're dealing with image data. Yes, there are other ways of turning images into vectors, but they are usually more related to kind of the image itself. And what we found out that as we move to kind of deeper and deeper networks, you move from the space of images that are identical pixel to pixel to a more common sense space, basically things that are kind of the same. So even if the images are of two very different teddy bears, they will be embedded relatively close to one another in the more sophisticated neural networks. Versus something like p-hash, where if the images are completely different, they will sit very far apart. Now, this was great, but we wanted to do better. And here's where we realized, wait, again, we can work really, really hard with a really sophisticated neural network to understand that two images from different angles of the same bear are the same thing. But this can be really, really hard. Who else has this problem? Well, our suppliers. And what they do is they basically pick different images of the same product and put it under the same product entity. So product entity defines similarity between images. And if product A and product B share a very similar image, they're probably linked, right? Or maybe even the same thing. And the same thing if product B and product C share an image, they're probably linked. But that also means that product A and product C are probably linked. This is transitive property, even if they don't share a single image that's similar. And this was really, really powerful because it kind of cracked the problem of product that had very, very different images of the same thing. So now that we have image similarity, and on top of that, the product links, well, what does the recipe says to do next? Well, take a clustering algorithm, cluster things together. But the more we tested different algorithms, we realized that there are some properties of clustering algorithms that were working kind of against us. And this is because clustering in general is global and agglomerative, and similarity is local and transitive. That's obvious, right? No, I'm just kidding. Of course, I will explain. So when I say clustering is global, what do I mean? I mean that it depends on the dataset. If you change the dataset a little bit, potentially products can move from cluster to cluster. And at least in my intuition, similarity for this problem is a very, very local property. If A and B are similar, they should always stay similar almost no matter what. And the second issue with the clustering algorithm, well, I want to say a lot of them are spherical. I know that's not true. That's an overgeneralization. You have things like dbScan or other algorithms that are really, really local and do really well. But at the end of the day, they tend to group things together even at the expense of the margins. So you will have cases where two products are very similar to one another, but they sit in different clusters for whatever reason. And going back to what I said before, I think similarity should be transitive and local, and this didn't really sit well. We had very, very strange results of products moving around, which didn't make a lot of sense to us. So what did we end up with? A new recipe. We start by looking at product images, but only the ones that were curated by the merchants. We take a neural network, extract embeddings, calculate cosine similarity, but we also use a good graph library instead of a clustering algorithm. And what we do, we take the embeddings, We maybe use the labels, well, sometimes just for filtering, but generally we discard them. And we overlay this with the product information that we have. And then we extract something called connected component, which is a very, very simple way of doing clustering. Basically, you look at all the things that have some similarity to one another, usually above a very high threshold, and just extract these groups without thinking too much about densities or other too many complicated things. And we had really, really interesting results. So what you see here, I call them gravity graphs. Basically, each dot is a product. Now, the order or the placement of the dots is completely random, but as you can see, dots are connected by black lines. These are links between products, and the more products get connected into one connected component, the heavier it gets, and the more it gets pulled toward the center. I also call these like galaxy graphs. So you can see when we set a really, really high threshold, like 100%, this means that the embedding vector has to be 100% match. So not image match exactly, but embedding match 100%. You can see that we already have quite a lot of products that got linked together into these kind of micro segments. And this is very likely exactly the same product, just under different SKUs. So we already got some interesting results. When we lower the threshold a little bit, allow a little bit of variation in the image, a lot more products get linked to one another, and you start getting slightly larger cluster that fall towards the center, but also around it, quite a lot of products and some products that remained, unlinked around the periphery. And of course, if you lower the threshold a little bit more, then almost immediately kind of everything collapses into one big tangled mess in the middle. It's actually pretty useful information because if you think about it, when you look at a category of products like, I don't know, teddy bears or gifts, if you find that you have some products that are not linked at all to any other product in the category, maybe they are outliers. It's one of the ways that we're thinking about kind of improving the catalog using this effort. So these kind of images were really useful. They helped us to do the hyperparameter tuning, and we ended up basically with this solution. And let's look at some really interesting examples. So can you tell me what's the common denominator between all these different product images? These are the main images. So we have a picture of a giraffe. This is a lovely place in Italy, a red umbrella, and an ape with headphones. How would you even start to see the connection, or how would you even start to understand that all of these images are of the same product? Well, in the background, they all share a version of one of these two images, either of the paint or of the paper, and these are all paint by number products. They were really, really popular when the quarantine began. So, we suddenly saw a rise So we suddenly saw an increase in sales, and it was really helpful for us to understand that even if the images are really different, we're able to make the link in the background using the secondary images. Now, it can get a little bit more complicated. If you remember the teddy bear from the beginning, it's actually made out of synthetic roses. And we have other products that are also roses, but crystal roses, and they shared an image of a rose in the background. So sometimes they would kind of stick together. And we had to make some decisions around that. But it also opened an interesting discussion about micro categories in the catalog. Instead of just like gifts, maybe we can do something that's related to flowers, or have like a rose-related collection that we can offer our merchants. So it opened a lot of really interesting discussions, and I want to say a much better understanding of the products in the catalog. So to conclude this talk, I want to leave you with some takeaways. First of all, scope. That was one of the most important keys. You have to be able to iterate faster. And I want to be a little bit provocative and say, sometimes as data scientists, the best thing we can tell our stakeholders is, listen, this will take a lot of time. This will not necessarily bring us the results we want. And maybe we should take all this time and effort that we would spend on, classifying and processing millions and millions of images on maybe improving our retention model. Maybe this will be a better ROI. And today, if I don't have this clear path of, first of all, solving the problem in small scale and then scaling up, which is what we did later, I want to say sometimes maybe you just need to say no and focus on something more productive. The second takeaway, out-of-the-box solutions prove to be really useful here. The only thing is you might have to be a little bit creative by the way you use them, so kind of don't stick to the recipe too hard and pick and choose whichever things work best for you. On that note, kind of pick the right tool for the right task. For our case, deep learning was really great for embedding vectors in a common sense space. It worked much better than other techniques, but the clustering algorithm, not great, or the labeling, not great. We just discarded them. And finally, the importance of domain knowledge. I think without the understanding of the dynamics of the catalog, of the way our merchants solve problem, of the way our retailers see the product, we would not be able to solve this. Just based on kind of taking a lot of images and throwing them onto an algorithm, that would never have worked. And it really helped us to solve the image quality problem, and it's also really helped us to solve the image similarity problem by looking at links between products rather than between images. So as I said before, it's almost always the secret sauce that will take your solution from good to great. And with that, I want to thank you for your time. You can find me on my webpage, on Twitter, and my HR would kill me if I wouldn't say that. We are hiring, so feel free to reach out or use the links from the presentation. Thank you very much.